Ever wonder why some chemical reactions are just, boom, explosive, while others can take literally years to happen? Well, it turns out we actually have a ton of control over that speed. So let's dive right in and figure out how we can become the masters of chemical reactions. To get us started, let's think about a question you've probably seen in your own kitchen. Why does a single sugar cube take forever to dissolve, but a spoonful of sugar disappears almost instantly? Or to put it in chemistry terms, why does crushing a solid into a powder make it react so much faster? Stick around because the answer to this one question is the key to this whole explainer.
And there it is. Believe it or not, the entire secret to speeding up or slowing down a reaction, it all comes down to one simple idea: collisions between particles. Now, this idea is so important, it's got its own name: collision theory. You can think of it as the master rulebook that basically runs every single chemical reaction in the universe. The first rule is super simple, almost common sense. For two particles to react with each other, they have to physically touch. They gotta bump into each other. If there's no collision, there's no reaction. It's really that simple. But, and this is a big but, as you're about to see, not every collision actually counts. So here's the crucial part. For a reaction to really get going, you need what we call a successful collision. And for that to happen, two things have to be true. First, yep, they have to collide. We got that. But second, they have to collide with enough energy. Chemists call this the activation energy. You know, a gentle little tap isn't going to cut it. They need to smash into each other with enough force to break their old bonds and form new ones. Okay, so this is where it gets really interesting. If we want to speed up a reaction, all we have to do is find a way to make more of those successful collisions happen every single second. And we can do that by turning a few control knobs. Today, we're going to look at the three big ones: temperature, concentration, and surface area. So let's start with the control knob we're all familiar with: temperature. I mean, you know this from cooking, right? You turn up the heat on the stove and your food cooks faster. That's a chemical reaction. But why does that work? Let's really think about it. Way down at the particle level. What is actually happening to all those tiny little molecules when we start cranking up the heat? Well, when you increase the temperature, you're basically just pumping energy into all those particles. They soak it up and get more kinetic energy, which means they start zipping around way, way faster. Now, when they're moving faster, they're obviously going to collide more often. But here's the real kicker. Because they have more energy, a much bigger chunk of those collisions are going to be hard enough to actually work. And that means we get way more successful collisions per second, which means a faster reaction. This is a perfect way to see it happen. In this experiment, a reaction is making the clear solution go cloudy. Now, if you did this on a hot plate, that solution would go cloudy almost instantly. But if you did the same thing in a bucket of ice, you'd be waiting a while. It's a perfect visual of a higher temperature giving you a higher reaction rate. All right, let's move on to our second control knob: concentration. The easiest way to think about this one is to imagine you're at a party. Is it easier to bump into someone when there are just 3 people in the room or when there are 30? It's the exact same idea in chemistry. So, what do you think happens to the speed of a reaction when you pack more reactants into the same space? If you said the reaction speeds up, you are absolutely right. When you increase the concentration, you're just cramming more particles into the same amount of space. They're literally shoulder to shoulder. And just like in that crowded room, collisions are going to happen way more often. And more collisions per second means more chances for a good one, giving us, you guessed it, more successful collisions per second. We can see this really clearly in an experiment like this one. So here, the reaction is making gas, and we're catching it in that syringe. If you use a really concentrated acid, you're creating a super crowded particle party down in that flask. They're going to collide like crazy, produce gas way faster, and fill up that syringe in no time. And that brings us to our third and final knob: surface area. And this brings us right back to that first question we asked about the sugar cube. See, when you have a big, solid chunk of something, the reaction can only happen on the outside surface. Most of the particles are trapped on the inside, just kind of waiting for their turn. But when you crush that solid into a powder, you've just massively increased the surface area. You've exposed all those particles that were hiding. With way more particles available to collide at once, the number of collisions goes through the roof, which means, say it with me, more successful collisions per second. Let's look at this setup here. We've got marble chips reacting with acid, which produces a gas. Because the gas floats away, the total mass on the balance goes down. Now, if you use big, chunky marble chips, that mass will tick down nice and slow. But if you swap those for the exact same mass of powdered marble, you've just upped the surface area big time. The reaction will fizz like crazy, and you'll see the numbers on that balance drop much, much faster. So, we've turned all 3 of our control knobs. What's the big takeaway here? Well, the takeaway is that you are now officially a master of collisions. You have the fundamental principle you need to control chemical reactions. So here's what I want you to remember. All of these things, temperature, concentration, and surface area, they're just different tools to get to the same goal. If you want to control the speed of a reaction, you have to control the rate of successful collisions. Turn up the heat, you get more energetic, successful collisions. Up the concentration, you get more frequent, successful collisions. Increase the surface area, you get more particles available for successful collisions. It all comes back to that one key idea.
So there you have it. That's collision theory in a nutshell. But don't let the learning stop here. Next time you're cooking or cleaning with something, or even just watching a piece of metal rust over time, think about what's going on at that tiny particle level. Now that you know the secret, where else in your own life do you see collision theory at work?